the school bus network problem. Dr. Lee, it's all yours.
Good afternoon, everyone. I'm Youngjae Lee, professor at the Department of Transportation and Urban Infrastructure Studies at Morgan State University. And this project is with Amireza Nikar, who has been my research assistant, who's going to get his PhD in this May. Hello, Amireza. Can you say hi?
Hello, everyone. Thank you so much for having me today. Thank you so much.
Okay. The topic of this presentation is developing an optimal integrated single framework algorithm for the multi-level school bus network problem, which was funded by UMac. I'm going to talk about the introduction and the background, and then Amireza will take over the methodology part, just like the previous presentation. The background of this research was my son attended Baltimore County Public School when he was in elementary school, middle school, and so on. So I became familiar with Baltimore County school bus system. Like many other school bus systems, the Baltimore County school bus system covers 3 different levels of schools: high school, middle school, and elementary school, with the same bus fleets. So their bell time is all different. High school first, so the school bus pick up high school students and then drop them at school, and then they go to pick up middle school students, and then they drop them at middle school, and then they pick up elementary school students, and then they go to the depot, and then in the afternoon they do the reverse way. They go to high school, pick up high school students, drop them at their home, and then go to middle school, pick up middle school students, drop them at their home, and then go to elementary school, drop them at their home, and then go to depot. So the same bus fleet covers many high schools, and then middle schools and elementary schools. And those algorithm, the routing algorithm for those 3 different trips are independently, separately kind of optimized. As far as I interview with the school bus, the transportation department for Baltimore County schools. So our motivation was, instead of making optimal routing for 3 different levels separately, maybe if we consider all 3 schools at the same time, if we consider them to make the algorithm for routings, then probably we can make a better algorithm, because more efficient algorithm, because when they leave the schools after dropping the students at schools, they have to choose the right schools to go to for the next round. So if we can consider 3 schools at the same time as an integrated single framework, we thought that we can improve the efficiency. So that was the background of this research. So as I mentioned, we tried to develop an integrated school bus problem, considers a sequential operation of fleet for all 3 levels in a unified a framework. Also, we considered identical reverse routes for morning and afternoon, and also considers separate routes for morning and afternoon. What that means is, well, when the school bus pick up students and drop those students at school, usually the bus drop those students in the afternoon in the reverse way. So if students are picked up first, they drop latest. If students are picked up latest, they drop the first. Usually because the school bus routing was identically reversed, morning and afternoon. But we also thought about if we can make the separate routes for morning and afternoon. If we optimize morning and afternoon separately, we can make the routes more efficient. So we also consider those two cases. So basically, we considered four different cases. The separate three routings for reverse routes, identically reverse routes, and three separate routes for morning and afternoon. So two cases for the independent three different routings, and also two different cases, identically reverse and separate routes for integrated a multi-level routing. So we um, optimized four different types of routings and then compare the result. We used simulated annealing algorithm for optimizing our a method, and the algorithm's objective is to minimize the total cost, including bus operating cost and total students travel time. So the importance of this research is the school bus system is essential. The public school a bus system is essential for many different states. Uh, and optimal routing can not only save operating costs, but also their students' travel time in the bus as well. We also considers a maximum travel time in the bus for students as well. So certain students don't suffer a lot of time in the bus, especially when they are close to their home. We use this degree of circular concept for many other our routing related researches, because uh, usually if we consider system optimal, there are some cases that certain part of the components here, students, needs to be sacrificed to make the system optimum. So to avoid those case situation, we try to provide their minimum travel time um, compared to their a shortest travel time, a, the ratio. So they don't stay in the bus, so they don't need to stay in the bus more than certain percentage of their a shortest travel time. So the Amireza will
Yes,
discuss about the methodology and mathematical programming. Amireza?
yes. Thank you so much. Actually, this our model has two main parts. In the first actually part, we define how many buses we have at the beginning of each time window. for example, we have for uh, morning trip, we have 4 different time uh, windows. The first actually one is from the actually buses from the hub to high school, and for the second one is from the high school to middle school, and the middle is school to the mm, actually on. So we have 4 different parts. So now in the first part, the uh, model tries to find how many buses we have at the uh, beginning of each time uh, windows, because for example for the time window 1 we have 1 hub, but in the second time window we have 2 high schools. So the uh, numbers of the origins are different in each time window. And in the second part, the uh, model tries to find the best actual route, so to mm, generates all of the uh, possible routes and find the optimal one. Next slide, please. So as we said, the uh, objective function of our model is to minimize the waiting time for uh, riders, and also the total traveled distance for the buses. Next slide, please. Yeah. Okay, so we have a lot of constraints in this model. So constraint 2 and 3 are for considering that each rider is actually served by mm, only one buses by only one bus, and the uh, constraint 5, 6, and 7 are to define the path for each actually bus. And also the constraint number 4, sorry, I think I missed that. It's for ensures that each bus is assigned to each school. Next slide, please. And here, constraint 8, and 9 ensures every route begins and ends from the school here, and constraint 10 and 11 finds total traveled distance up to rider I of school S. And constraint number 12, the next slide, please. And constraint number 12 defines the arrival time of the buses, and the constraint number 13 is actually defines the waiting time for each rider. Constraints number 14 and 15 are related to time ratio constraint here, and the seven and the actually the 16 is based on the is related to the cycle time, because we have one actually hour of uh, serving for each levels here, for high school, for middle school, and so on. The next slide, please. So the 17 is related to the capacity of the buses here, and 18 the is related to defining the total travel uh, distance here by buses. So the next slide, please. Okay, so here we have uh, an example here to actually show the um, efficiency of our developed model. We have 720 uh, students here in three levels. Two higher schools we have, three middle schools we have, and four elementary schools. So, and one depots. So, and the fleet size here is 12 buses, and also each bus has 30 seats, and the average speed of each bus is 30 kilometer per hour. Next slide, please. Okay, here we have two main actually time window here. Each time each actually one has four separate time window here. So if you look at the picture on the left, you will see that the bus has one deadhead trip from 6 to the location of the first riders in, for example, high school 1, and then for the next actually one, and then to the next one, and it goes to the uh, high school 1, and then for middle and elementary, and then it actually has one uh, deadhead trip to the to its origin, to the actual depot. So it starts at 6 and ends at 10. So we have actually four different time windows here. But in the uh, uh, afternoon, we will have again the one deadhead trip to um, um, high school 1, but the point here is that we don't know the order of dropping off of riders here. It actually can be the rider number 2 or 3. We don't know here. So it's the a big uh, picture of our actually methods here. So the next slide, please. So here we have two the pseudo-code actually for our models. The models in the left side is related to finding the uh, available buses in each time window, and the other one in the right side is uh, related to finding the optimal routes. Next slide, please. Okay, here we have different uh, uh, figure for three actually types. In the left side up, we have the this is one example for middle school number one. This is only for actually that, because we have many schools here, and so this is just for actually that. So the in the left side, the down, you actually see that the uh, uh, routing, when the uh, routing is the actually same in uh, morning and afternoon. For example, if the passenger, if uh, rider one picks up at the first at morning, then the bus will drop off him first at evening. And also in the right side top, the routing for the morning we have, and also we have in the right side down, when the routes are not this same in the afternoon. The routings are not the same as uh, morning here. So the next slide, please. Okay, here yours, Dr. Lee. Uh, Dr. Lee, do you want to talk about it, or I
Yes,
cover?
I'm
Okay.
going to. The next slide is about the summarized result of the model. This is more specific one, but the next one is summarized one. So probably I'll use this one for this one. As we can expect, I mean, the result is pretty much expectable, because when we use three separate model, the routings, the algorithms with same routing for morning and afternoon, um, which are identically reversed one, is least efficient one. And if we use integrated framework, we can save cost. If we use morning and afternoon routes differently, then also we can save cost. And eventually, if we make a single integrated framework with different morning and afternoon routing, then we can save the cost the most. So here, compared to basic case, which is three separate levels of algorithm with uh, the same morning and afternoon identically reversed routing network, compared to that basic network, if we use integrated framework with a different morning and afternoon routing, then we can save about 12.5% cost reduction for this hypothetical network. Um, we wanted to use the real data, but the students' data is very a sensitive data, so we couldn't use it. So we made a hypothetical network, but all the cost saving is obvious. Just this research shows that um, this kind of a integrated framework with for different morning and afternoon routing is doable, and it can save some meaningful amount of cost savings. So the contribution of this research is the, a to show that making this kind of algorithm is doable, and the cost saving is meaningful. The conclusion is the total cost of integrated single routing framework for different morning and afternoon made the biggest cost savings. And so when the, the transportation department for public school, when they consider a school bus routing, probably if they utilize the same fleet for 3 different levels of schools, then it is worth to consider integrated a single framework routing algorithm to save more cost. Also, making morning and afternoon different routes can save us a cost, can make us a cost savings as well. This research was supported by the UMAC and USDOT, and we'd like to appreciate their support once again. So our presentation is rather short. This is Friday afternoon, so we're happy to finish our presentation fast. And if you have any questions, we'll be happy to take any questions. Thank you.
Thank you very
Thank you
much,
so
Dr.
much.
Lee. Thank you. Questions? I know everyone is tired and it's Friday afternoon. But any questions? You can also ask them later if you think about it later, and you can email Dr. Lee or Amireza.
Yeah. We'll be happy to take any questions later.
Hey, I have a quick question. This is Dr. Pitts.
Yes, Dr. Pitts.
Hey, I just wanted to ask which softwares are you using to run your models? Are you generating your models manually for your LPs here, or are you doing them automatically or manually?
Hello. Actually, we used MATLAB, the platform of our actually work. So we didn't use any sorts of simulation software here. It's uh, uh, purely based on the actually codes. So that's what we did. It's actually pure actually codes.
Yeah, those a the algorithm is a algorithm use simulated annealing, which
Okay,
was created in MATLAB.
I see.
So Amireza coded in MATLAB for simulated annealing, and we ran the software, does the MATLABs.
Okay, all right, great. Thank you.
No problem.
Thank you.
Okay, thank you everyone for attending our UMake webinar series of this month. We will have next month, most probably going to be April 30th, and it's on CAV, Connected Autonomous Vehicles and Energy. Thank you everyone for attending today, and thank you for the presenters for their nice presentations, and we hope to see you next month. Have a great weekend.